Okay, hello everyone. My name is Seong Ki Yoo. I'm a lecturer in electronics engineering and an associate member of Center for Data Science at Coventry University in the United Kingdom. Today, I will present wireless communication techniques for autonomous unmanned vehicles. Just before we begin the main body of the presentation, I will briefly introduce autonomous unmanned vehicles. Following from this, I will talk about some of the challenges for future autonomous vehicles. Then I will go on to introduce vehicle to everything, which is known as V2X communication techniques. Here I will talk about what is V2X, how does V2X work, and some application of V2X. Then I will present two channel studies recently performed in the UK. These include V2P communication channel modeling and distributed antenna system for V2P communication. Then finally, I will draw the presentation to a close with some concluding remarks. Okay, what is unmanned vehicles? As its name implies, this is a vehicle without a person on board. A manned vehicle can either be remote control vehicles or autonomous vehicles which are capable of sensing their environment and navigating on their own. As shown in this diagram, unmanned vehicles include many different vehicles such as modern drone, General Atomics MQ-9 Reaper, construction machines, modern car, underwater drone, and so on. And this can broadly be segmented into unmanned aerial vehicle, unmanned ground vehicle, and unmanned underwater vehicle. While unmanned vehicles originated mostly in military applications, their use is rapidly expanding to commercial, scientific, recreational, agricultural, and other applications. Due to diverse range of applications, unmanned vehicle market has been growing. For example, the UAV market is projected to grow from 19.3 billion US dollar in 2019 to 45.8 billion US dollar by 2025. As you can see this diagram, unmanned ground vehicle market is projected to grow from 2.7 billion US dollar in 2018 to 7 billion US dollar by 2025. Okay, how about unmanned underwater vehicles market? As you can see from this diagram, this is projected to grow from 2.6 billion US dollar in 2016 to 5.1 billion US dollar by 2022. Among these three areas, today in this presentation, I will focus on autonomous unmanned ground vehicles. Okay, let's have a look some of challenges currently exist in autonomous vehicle area. The challenges can be broadly divided into technological challenges and non-technological challenges. And the former includes in-vehicle sensors, software, and algorithm, whereas the latter contains law, policy, and ethics. Since we are all researchers, I'm pretty sure we are more interested in technological challenges. And then I came up with one important question, which is, can people trust autonomous vehicle? Okay, let me introduce two interesting surveys. The first survey has revealed motorists in the UK are not trusting enough to surrender control to self-driving cars. More specifically, less than a quarter of drivers would be willing to take their hands off the wheel in the vehicle designed to control itself. And this is the same in other countries. When we look at the second survey, it says that 54% of US drivers feel less safe sharing the roads with self-driving cars, and 78% of US drivers are afraid of riding a self-driving car. And to be honest with you, I'm a little bit shocked with this research, and I thought researchers like us need to change this. One of the reasons why people don't trust self-driving car is currently not safe enough for them to trust. Consequently, we need to increase safety for the widespread adoption of autonomous vehicle. Okay, how can we improve the safety? This diagram shows typical in-vehicle sensors used in autonomous vehicles. For a car to be autonomous, the car requires sensors to collect information about the road and a central processing unit to analyze all the data and make decisions appropriately. Here, as shown in this diagram, in-vehicle sensors include lidars, radars, cameras, GPS, and ultrasound. These sensors will be used to recognize the vehicle's surroundings and measure the distance between the vehicle and nearby objects, so the central processing unit can evaluate them and respond accordingly. And actually, these technologies already exist. For instance, park assist, lane keep assist, automatic emergency brake, and forward collision warning, and so on. However, there are many problems with consistently identifying objects. For example, rain, snow, roadworks, complexity driving, and other obstacles which can prevent the vehicle from carrying out the correction driving action. There are many other techniques available, but I believe that wireless communication techniques will play an important role in autonomous vehicles to overcome these problems. I believe that many of you already heard of vehicle-to-everything communications, which known as V2X Communications. V2X communication technologies allows vehicles to directly communicate with each other, pedestrians, roadside infrastructure, and network or cloud to deliver an array of benefits in the form of road safety, traffic efficiency, smart mobility, environmental sustainability, and driver convenience. And most importantly, V2X is helping pave the way for fully autonomous driving through its unique non-line of sight sensing capability. This allows vehicles to detect potential hazards, traffic and road conditions from longer distance and sooner than other in-vehicle sensors. And as you can see this diagram, V2X can be broadly categorized into four different groups, namely V2V, so vehicle to vehicle, and V2I, is vehicle to infrastructure, V2P, the vehicle to pedestrian, and lastly V2N, vehicle to network. This diagram shows some examples of V2X capabilities, and these include do not pass warning, 0 mile per hour blind curve or local hazard warning, roadworks warning, vulnerable road user alerts at blind intersection, intersection movement assist at blind intersections, and lastly, left turn assist. Okay, when we look at do not pass warning, this warns the vehicle it's not safe to pass a slower moving vehicle if the passing zone is occupied by another vehicle using vehicle-to-vehicle communications. And also for roadwork warning, the vehicle can receive information about roadworks including lane closures from roadside infrastructure or network or vehicles. As we know, the performance of any wireless system is heavily dependent upon the channel on which it operates. Therefore, a fundamental understanding of propagation mechanism encountered in V2X communication is crucial for the success of future autonomous vehicles in which information is efficiently and securely transferred between wireless devices. I'm now going to present the findings of some V2X channel studies performed here in the UK. These include V2P channel modeling and distributed antenna system for V2P communications. As you already noticed, among 4 different types of V2X communications, I focus on V2P communication channels. Okay, let's begin with V2P channel modeling. Pedestrian-to-vehicle communications and also the reciprocal vehicle-to-pedestrian communication are important part of vehicle-to-everything communications. As shown in this diagram, these occurred when a wireless device is situated on a person or pedestrian communicate with wireless devices located on the vehicle. They have gained much attention recently because they will enable direct communications between vehicles and vulnerable road users, including pedestrians and cyclists. And for example, P2V communications have been used as the basis for a collision avoidance system and a pedestrian protection system. Additionally, they may act as relay nodes for one another, and thus provide multi-hop communication in case of wireless device existing outside their communication range. The propagation conditions encountered by both wearable and vehicular communications are known to be particularly challenging. For example, wearable devices operating in a range of different environments are subject to complex antenna body electromagnetic interaction effects. And due to the low elevation of at least one end of the link, the wearable devices are subject to frequent shadowing events caused by the user's body and the bodies of other persons in the local surroundings. In a similar manner to wearable communications, vehicular communication can take place within diverse environments ranging from rural areas, highways, and interstates through to densely and sparsely populated urban zones. And furthermore, these often occurred at high velocities and in the presence of other moving vehicles, which can result in significant scattering and obstruction of the link. Like antennas operate in close proximity to the human body, within vehicular communication, the antenna-vehicle interaction effects can have a considerable impact on the performance of communications. As mentioned earlier, it is crucial that we build detailed models that can be used to accurately characterize its behavior. Consequently, in this study, the pedestrian-to-vehicle communication channel has been investigated within urban environments at 5.8 GHz. Okay, let me introduce the measurement system used for the P2V channel measurements in this study. The measurement system consists of 5 bespoke wireless nodes that operate as 5.8 GHz. All nodes were capable of operating as either a transmitter or receiver, but for the purpose of this measurement campaign, one was configured as a transmitter, and the remaining 4 were configured as RX nodes. Each wireless node consists of 2 different parts. So the first part is RF section, which featured an ML5805 transceiver chip manufactured by RF Micro Devices. And the second part is a baseband controller section, which contains a dedicated PIC32MX microcontroller manufactured by Microchip Technology Incorporated. The node acting as transmitter was pre-calibrated using Rhodium-Schwarzschild power meter and was configured to transmit a continuous wave signal at 5.8 GHz with an output power of plus 17.6 dBm. So when acting as a receiver, the baseband controller was programmed to sample the received signal strength from transceiver chip using a 10-bit ADC converter. And all of the RX nodes were also pre-calibrated using a Rhodium-Schwarzschild vector signal generator. So the RX nodes simultaneously logged the RSS sampled at a rate of 10 kHz on a single laptop in real time, which was also equipped with a GPS receiver to record the position of the vehicle. And the antenna type used by both transmitter and receiver nodes was a omnidirectional sleeve dipole antenna with gain of 2.3 dBi. As you can see here, the transmitter was mounted using Velcro in a vertically polarized orientation, parallel to the front central chest region of an adult male of mass 75 kg and height 1.72 meter, which results in an antenna height of 1.2 meter above the ground level. And please note that GPS receiver was also carried by pedestrians so that their position could also be monitored throughout the measurements. Okay, as you can see the diagram on the right hand side, we have the measured antenna directivity patterns for the chest-mounted transmitter. So from this directivity pattern, we can make the following observations. So firstly, the presence of pedestrian's body reduced the forward antenna directivity by as much as 12 dB. And secondly, the antenna directivity also decreased dramatically around the back of the pedestrian's body as a direct result of body shadowing. As you can see the diagram on the left-hand side, we can see 4 antenna positions on the vehicle which were considered for this study. And these were the front center and rear center of the roof, and on the left wing and right wing mirrors of vehicle. And it should be noted that all receiver antennas were mounted on a vertical polarized orientation. The roof-mounted RX nodes were secured directly onto the vehicle's body. However, due to the physical dimensions of the RX nodes, the base of the antenna maintained a distance of 30 mm from the roof surface. On the wing mirrors, the antenna was mounted on the outside edge of the wing mirrors to imitate the placement of the antenna inside the wing mirrors unit while maximizing the signal coverage. The measured antenna directivity patterns for the RX nodes mounted on the vehicle's roof and wing mirrors are presented in the diagram on the right-hand side. It is clear that the wing mirrors antennas are subject to significant amount of shadowing caused by the vehicle in the direction opposite to which they are mounted. Otherwise, they have comparable directive patterns to the roof positions on their unobstructed side. All of the measurements conducted in this study were performed in the Titanic Quarter of Belfast in the UK. And as shown in this diagram, the surrounding area contained a number of large office buildings situated at various distances and orientations related to the roadside. This particular setup was chosen to isolate the effects of the vehicle and the pedestrian's body on the P2V channel. The vehicle's trajectory was limited to the straight stretch of the road. However, as is typical within urban environments, the vehicles may travel along the near side or the far side of the road related to the pedestrian. Moreover, as the vehicle travels along the road, the pedestrian may adopt one of two states, namely stationary or walking along the roadside. Therefore, as indicated in the following diagram, we consider 4 different scenarios in this study. Okay, scenario A. The pedestrian stood stationary, parallel to the roadside, and oriented towards the direction of the oncoming vehicle, which it traveled on the side of the road close to the pedestrian. Okay, scenario B. Similar to the scenario A, the pedestrian stood stationary and parallel to the roadside. However, in scenario B, the pedestrian oriented away from the direction of the oncoming vehicle, which he traveled on the side of the road furthest from the pedestrian. Unlike scenarios A and B, in scenario C, the pedestrian walked parallel to the roadside and oriented towards the direction of the oncoming vehicle, which is simultaneously traveled on the side of the road close to the pedestrian. Okay, lastly, scenario D. The pedestrian walked parallel to the roadside and oriented away from the direction of the oncoming vehicle, which is simultaneously traveled on the side of the road furthest from the pedestrian. This plot shows the raw received signal power for 3 of the receiver nodes mounted on the vehicle as function of separation distance between transmitter and receiver obtained during scenario A. Please note that the rear center node was largely indistinguishable from the front center node when plotted on this scale. Therefore, the rear center node has been omitted for clarity. Okay, as expected, the P2V channels experienced significant signal fluctuations, which varied according to the vehicle's position related to the pedestrian. In particular, it was apparent that the channels underwent different fading conditions before and after the vehicle passed the pedestrian. As a result of this observation, we segmented our data into two different regions, namely the approaching and receding regions. As the vehicle traveled into receding region, the effect of body-induced shadowing can be observed to cause an immediate reduction in the received signal power of the front center and left wing channels, so in excess of 20 dB. And moreover, the combined shadowing effect of both the pedestrian and vehicle had an even more detrimental impact on the right wing channel. Consequently, the fading that occurred within this region often expanded into the noise floor at the extremities, and therefore we limited our data analysis beyond this point to the maximum distance of 50 meters behind the pedestrian for all scenarios. In order to understand the propagation mechanisms that affect P2V communication channels, we have decomposed the received signal power into its path loss, large-scale fading, and small-scale fading components. Using this approach, the received signal power can be modeled by following expression. To extract the combined path loss and large-scale fading from the received signal power, the fluctuation due to small-scale fading were removed from the received signal power. Following the removal of the small-scale fading, as an example, this plot shows the combined path loss and large-scale fading components along with the received signal power for the front center channel during scenario A. In part of the approaching region, we can observe that the combined path loss and large-scale fading fluctuation exhibit a notice of quasi-periodicity. This artifact is usually indicated of a few strong signal paths interacting to cause constructive and destructive signal attenuations at the receiver. Typically, in vehicular communication channels, this phenomenon is modeled using the two-ray ground reflection path loss model, as shown in this diagram. In this model, the received signal consists of two components, which are the line of sight component that is just a transmit signal propagating through the free space, and a reflected signal component that is the transmit signal reflected off the ground. So therefore, using the superposition of these two components, the two-ray ground reflection path loss can be expressed as follows. In this expression, delta pi denotes the phase difference between the two signal components, and GL and GR are the both a product of transmitter and receiver antenna gains for the line of sight and reflected signal path. And this plot shows the two-ray ground reflection path loss model superimposed over the received signal power and combined path loss and large-scale fading signal of the front center channel during scenario A. As you can see, there are striking similarities between the combined signal fading and path loss model in the approaching region. This was hardly surprising, since the front central channel during this region maintained an optical line-of-sight path with a chest-mounted transmitter, along with an unobstructed view of the road surface between the vehicle and the pedestrian. However, as the vehicle nears the pedestrian and moments after passing them, the received signal power actually increased compared to what would normally be expected if considering free space propagation. This was consistent observation throughout the measurement trials conducted in this study, and will likely be an important feature of future P2V channels. It is attributed to the strong enhancements caused by the vehicle's metallic structure, whereby signal contribution that may ordinarily be lost due to free space propagation are returned towards the receive node. The net result of this is an increase in the average received signal power. As the vehicle processed through the receding region, where the body shadowing becomes more prominent, it was evident that the two-ray ground reflection model provides a poor approximation of the fading which occurred within this region. On a closer inspection of the combined path loss and large-scale fading signal, a more frequent quasi-periodicity than predicted by the two-ray ground reflection model was evident. This suggests that for this particular section of the front central channel, a higher order array model could provide a better approximation of the path loss. Due to the inability of two-ray ground reflection model to accurately characterize the path loss over all of the considered channels and all of their constituent region, we elected to adopt a more uniform and practical approach to model the path loss, which is now detailed in the next slide. The path loss experience in a fading channel can also be modeled in logarithmic form using the following expression. In this expression, D denotes the separation distance between the transmitter and receiver. D0 is the reference distance, and PL0 is the path loss at the reference distance. Lastly, eta represents the path loss exponents, which is related to the propagating environment. As you can see, black continuous line, it is obvious that a calculation of the path loss based on the free space model provides a poor overfit to the measurement data. For this reason, we persist with the dual slope path loss model and denotes the sections as near and far with respect to the pedestrian. Therefore, by applying these distance constraints, the path loss is now defined using a dual slope path loss model, and this is given by the following expressions. Here, eta and eta f are the path loss exponents for the near and far regions respectively, and this is the critical breakpoint distance, or simply breakpoint distance, which means the point where the data are segmented. In this analysis, as the vehicle passes the pedestrian at varying distances in each scenario, we chose the minimum separation distance between transmitter and receiver for that scenario as the reference distance. And in order to obtain the path loss parameters in dual slope path loss model, linear regression was performed on the combined path loss and large-scale fading signal. Prior to performing the model fitting, the combined signal must be segmented at the breakpoint distance, which is typically estimated as the first planar distance, that is, where the first planar zone touches the ground. However, due to the unique geometry of P2V channels, it was immediately evident that the optimum breakpoint distance was significantly closer to the pedestrian. So in this study, the breakpoint distance was selected by estimating the breakpoint distance by jointly optimizing the near and far slopes simultaneously. This was achieved by incrementing the breakpoint distance in steps of 0.05 meter from the minimum to the maximum distance within each region, while performing linear regression for both slopes at each distance and recording the joint residual error. So therefore, the breakpoint distance could be easily identified as the point where the combined regression error was lowest. And it should be noted that the far slope linear regression fit was constrained at the breakpoint distance to ensure the continuity of the path loss model. Okay, as an example, this plot shows the combined path loss and large-scale fading signal with a superimposed resultant estimated path loss model for the front center channel during scenario A. And here, for both approach and receding regions, black dashed and continuous lines represent near and far region, respectively. As you can see, this process of estimating the breakpoint distance provided an excellent fit to the combined path loss and large-scale fading, which was superior to the single slope and two-ray ground reflection models. And as an example, this table shows parameter estimates for the path loss model for scenario A. And these include path loss exponents for the near and far region, and breakpoint distance, reference distance, and path loss at reference distance. And here AF, AM, RN, and RF denote approaching far, approaching near, receding far, and receding near, respectively. In this scenario, the pedestrian was oriented towards the oncoming vehicle, and as a result, the approaching region contained no body-induced shadowing. So from this table, with the exception of the left wing channel, the path loss exponents between the approaching far and approaching near region showed significant disparity. In the approaching far region, the path loss exponents were reasonably close to those anticipated in free space, ranging from 1.53 to 2.18. However, when the vehicle entered the approaching near region, the path loss exponents obtained for the front center and rear center mounted devices increased significantly, reflecting a rapid increase in received signal power as the vehicle traveled close to the pedestrian. As discussed previously, this observation was caused by the vehicle's metallic structure, returning considerable amount of signal power in the direction of the pedestrian, which would be ordinarily have been lost in free space environment. As anticipated from the characteristic of the antenna directivity pattern, which is shown in previously, The path loss exponents for the right-wing channel decrease at close proximity to the pedestrian as a result of reduction in the received signal power, which is caused by the increased shadowing of the direct signal path induced by the vehicle. And this reflected in negative path loss exponents obtained for right-wing channel. When the vehicle passed the pedestrian, it moved into the shadowed region behind the pedestrian's body. Similar to the approach near region, there was substantial drop-off in the received signal power with the distance. That is, as shadowing effects of the vehicle structure on the direct signal path increased. In the receding far region, with the exception of the right-wing channel, the reduction in the received signal power was in line with that for the approaching far region. Interestingly, although the left-wing channel contained no vehicle-induced shadowing for this scenario, the body-induced shadowing alone still resulted in a substantial power drop-off over the distance in this region, directly behind the pedestrian's body. Okay, now let's move on to the next topic, which is about distributed antenna system for V2P communications. In pedestrian-to-vehicle communications, as we already find out in previous study, wireless devices are operated in close proximity to the human's body and vehicle's body while they are mobile. In this case, the direct signal path between the pedestrian and the vehicle is generally obstructed by pedestrian's body and/or vehicle's body. Due to these shadowing effects, a line-of-sight link between the pedestrian and vehicle is not always available. Under non-line-of-sight channel conditions, it is well known that deep fade can occur in the received signal power, which can reduce the overall signal reliability and the performance of P2V communication systems. One approach which is often employed to overcome signal degradation caused by propagation-related effects is the use of the distributed antenna system. The use of specially separated antennas in vehicular networks provides many advantages, such as higher packet reception rate and an improvement in the overall received signal strength. So, motivated by this, in this study, we investigated the possible signal reliability improvement for P2V communication channels operating at 5.8 GHz using distributed antenna system in conjunction with switched combining techniques. In switched combining schemes, the distributed antenna system selects one of the available antennas according to a corresponding criterion, and this contains pure selection combining, switch and state combining, switch and examine combining, and switch and examine combining with post-examine selection. It is widely known that among the aforementioned switched combining schemes, the switch and examine combining with post-examine selection, which is known as SEPcs. This scheme provides almost the same performance with less complexity compared to pure selection combining scheme when the optimum switching threshold is selected. So therefore, we consider the use of SEPcs based distributed antenna system in this study. Okay, Let's see how SEPcs based distributed antenna system is working. As you can see this diagram, the system persists with current antenna when the receive SNR is above the predetermined switching threshold. On the contrary, when the receive SNR falls below the switching threshold, the system switches from current antenna to another antenna and then examines the receive SNR. If this is not above the switching threshold, the system again switches to another antenna and examines its received SNR. This process continues until the system either finds an acceptable antenna or determines that the received SNR at all of the antennas are unacceptable. In the latter case, the system will take full advantage of the fact that all available antennas are examined. So consequently, the system will select the best performing antenna from those available. That is the antenna which experiences the highest received SNR. Measurement system. As you notice, the utilized TX and RX nodes were the same as those used for the first channel study, so therefore I will skip this slide. Okay, as you can see from this diagram, for the hypothetical distributed antenna system, antennas were positioned at 6 different locations of the vehicle exterior. And these are front center of the roof, left wing mirror, right wing mirror, rear center of the roof, rear left of the roof, and lastly, rear right of the roof. And it should be noted that all of these antennas were mounted in a vertically polarized orientation. These on-vehicle locations were chosen as candidate antenna mounting position for distributed antenna system used in future vehicular application. And the vehicle used for the measurements was a typical European small 3-door hatchback car. Again, all of the P2V channel measurements were performed in the Titanic Quarter of Belfast in the UK. And we consider two different movement scenarios in this study, namely stationary and walking. Okay, in the stationary scenario, the pedestrian stood static and parallel to the roadside while oriented towards the direction of the oncoming vehicle. And in the walking scenario, the pedestrian walked parallel to the roadside and again oriented towards the direction of the oncoming vehicle. For both stationary and walking scenarios, the vehicle traveled on the side of the road close to the pedestrian. And during the measurement, the pedestrian walked with a velocity of approximately 1.2 meters per second, covering a distance of 15 meters. In accordance with UK traffic laws for the single carriageway road, in both stationary and walking scenarios, the vehicle maintained a velocity of 13.4 meters per second, or equivalently 30 miles per hour, while traveling in the left-hand lane. And prior to data analysis, the received signal power was transformed into the received SNR, as shown in this plot. The potential improvement in the received signal reliability that could be achieved using the SEPcs based distributed antenna system was evaluated using the measured diverse gain. In this study, we defined the diverse gain as the improvement in the received SNR at the output of the distributed antenna system compared to the received SNR at the target antenna for a given signal reliability. For the purpose of the investigation performed here, antenna 1, that is the front center roof, was considered as the target antenna, and all diverse gain calculations were made at a signal reliability of 90%. In this study, we considered 4 different groupings of the antennas. As you can see this diagram, these are Group 1, a dual antenna configuration which consists of antenna 1 and antenna 4. And Group 2 is another dual antenna configuration consisting of antenna 2 and antenna 3. And Group 3, a 3 antenna configuration which consists of antenna 4, antenna 5, and antenna 6. And lastly, Group 4, another 3 antenna configuration consisting of antenna 1, antenna 2, and antenna 3. This plot shows the diverse gain achieved by each of the distributed antenna system groupings for different switching thresholds, ranging between 0 dB and 50 dB across the 2 different scenarios, namely stationary and working. It is clear that the achievable diverse gain highly depends on the switching threshold, but there exists an optimal switching threshold which maximizes the achievable diverse gain. For example, when the optimal switching threshold is selected for the stationary scenario, the diverse gain for groups 1, 2, 3, and 4 were 3.1 dB, 4.5 dB, 3.2 dB, and 7.2 dB respectively. And interestingly, the negative diversity gains are also observed at very low switching threshold region for groups 1, 2, and 3. This indicates that there was no benefit to using a distributed antenna system with these switching thresholds. When comparing Group 1 and Group 2, Group 2 provided a higher diverse gain than Group 1 for the stationary scenario, whereas Group 1 offered a higher diverse gain than Group 2 for the working scenario. And when comparing Group 3 and Group 4, Group 4 outperformed Group 3 for both stationary and working scenarios. This is most likely due to the fact that each antenna experienced different levels of shadowing according to the antenna position on the vehicle and pedestrians' movement. As a consequence, the achievable diverse gain depends on not only different movement scenarios, but also different groupings of the antennas. Interestingly, when comparing Group 1 and Group 3, that is, comparing a dual antenna configuration and 3 antenna configuration, so actually there was no significant benefit obtained from including the additional antenna. This was possibly due to the fact that antenna 1 exhibit higher average SNR compared to those for antenna 4, 5, and 6. And this suggests that the P2V channels between the chest-mounted transmitter and the rear roof-mounted receivers were particularly prone to the shadowing effects caused by pedestrian's body and/or vehicle's body. On the contrary, when comparing Group 2 and Group 4, that is, comparing another dual antenna and 3 antenna configuration, so diverse gain increased from 4.5 dB to 7.2 dB, and from 1.9 dB to 5.5 dB for the stationary and working scenarios respectively, which demonstrate that the addition of further antenna to the distributed antenna system can still provide worthwhile gains. To visually investigate the effect of different switching thresholds on the number of executed path examinations, this plot shows the average number of path examinations as function of the switching threshold for all of the scenarios and groupings. As expected, the average number of path examinations was found to be 1, at very low switching thresholds for all of the considered groupings. As the switching threshold increases, the average number of path examination tends towards the number of available antennas, that is, 2 for Group 1 and Group 2, and 3 for Group 3 and Group 4. When comparing all of the considered groupings, the average number of path examination for Group 3 was slightly greater than those for the other groups to achieve the maximum achievable diverse gain. Before we wrap up, I will summarize the main findings of these two channel studies. To characterize the propagation mechanism which are responsible for shaping the received signal in the P2V channel, we decompose the received signal into its path loss, large-scale fading, and small-scale fading components. Then we show that although there was evidence of interference caused by multiple rays interacting with one another, the popular two-ray ground reflection path loss model was unable to accurately describe the compounded effects of the vehicle and pedestrian's body on the signal attenuation in the majority of the considered scenarios. Instead, we find out that the overall path loss was well characterized using a dual slope log distance model, which enabled us to distinguish between different path loss characteristics experienced at close proximity to the pedestrian and further away. Also, the potential improvement in the received signal reliability for P2V communications at 5.8 GHz using dual and 3 antenna SEPcs based distributed antenna system has been evaluated in terms of diverse gain. It was found that using the SEPcs based distributed antenna system improved the overall signal reliability by as much as 7.2 dB when an appropriate switching threshold was selected. Although I only presented P2V channel studies today, the approach or methodology used in these two studies can be applied to other V2X communication channels, as well as unmanned aerial vehicle and unmanned underwater vehicles channels. Okay, this is the end of my presentation today. Thank you.